Hello, everyone, and welcome to the Tasmanian Institute of Agriculture's Future Forum. Today, our theme is ensuring a sustainable future for Australians' ruminant livestock production. Firstly, as a reflection of this institution's recognition of the deep history and the culture of this island, I would like to first acknowledge the traditional owners, the Palawa people, and the custodian of the land upon which we meet, and pay respect to elders past, present, and emerging. My name is Ape Omede, and I am a lecturer in animal production at the Tasmanian Institute of Agriculture. I am also a committee member of the Australian Association of Animal Sciences, Victorian and Tasmanian branch. We're also joined today by the collaborators for this webinar for today, which is the Australian Association of Animal Sciences as well. So each year, the Tasmanian Institute of Agriculture interacts with hundreds of people through different kinds of workshops, presentations, field trips, all across Tasmania. We know that not everyone is able to join us on farm, so we're offering everyone here today a front row seat in this virtual forum, so that we can connect with you and you can connect with us as well as the expert that we have today to explore issues related to the future of agriculture in Tasmania and, of course, across Australia. Before we kick off today, let's just have a few housekeeping notes. Your microphone, camera, chat function, and raised hand function have all been disabled so that the speakers will be able to concentrate on their presentation. But we do encourage you to ask questions, and this can be done at any time by typing your question into the question and answer function that you'll see on your screen. You can ask questions anonymously, and the selection of these questions will be answered during the question and answer session towards the end of today's forum. If you're addressing your question to any of the speakers specifically, it would be good for you to make a note on that so that we can direct them to the appropriate speaker that you want to respond to your question. And finally, I'd like you to know that this forum is being recorded, and the recording will be made available to be viewed on our YouTube channel after the forum, and also an email will be sent out to let you know when that is ready. So today we're exploring the pressing need to find a solution to livestock methane emissions, and our speakers will address this challenge and possibly provide insights and ways to mitigate the issue of methane emissions in livestock production. And this will be done while discussing their presentations. And that will give us some insight on what the future could look like for livestock producers, not just in Tasmania, but all across Australia. So I'd like to quickly introduce our first speaker for today. Our first speaker for today is Dr. Joe Newton, the of the Victorian and Tasmanian branch of the Association of Animal Sciences, and currently works as a research scientist for Victoria Agriculture Victoria, where she uses a multidisciplinary approach in developing and valuing decision support tools that enable more informed breeding and management decisions on farm. Thank you, Joe, and I'll hand over to you to kick off your presentation.
The Australian Association of Animal Sciences is delighted to be collaborating with TIA today on our future forum. I know that everyone's really tuned in to listen to Matthew and Fran talk today, so I'll keep this short and sweet. The Australian Association of Animal Sciences is the professional association for animal scientists, consultants, industry professionals, and students in Australia. AAAS is then also a member of the World Association for Animal Production and the Asian Australasian Association of Animal Production Societies, as well as the British Society of Animal Sciences. Well, what does AAAS do? We help build industry capacity by providing a support network for members, access to scientific research, professional development opportunities, links to our member network, and local and national events. What does that look like in practice? Well, we have a significant scholarships and awards program at the moment. We've got 11 scholarships and counting to support attendance at our 2024 Congress. We award 2 international travel awards annually, and you can see photos from last year's recipients, Emma and Mariano, at their conferences. We also sponsor early career scientists and student awards and have a AAAS fellowship scheme. In addition to online webinars and seminars like we're all attending today, AAAS has 5 regional branches that support local activities, a mixture of in-person and online events. And you can see some of our recent events, donuts and discussions down in Dookie in Victoria. The Wagga branch recently held a barbecue. We had a breakfast at the Northern ICMJ event last year. I know the Wagga branch has also booked the lecture theatre to live stream today's webinar as well. And just last week at Beef Week, our AAAS Queensland and Northern Territory branch ran a social activity there. Probably the highlight event on the calendar is our Animal Science Conference, which is held every 2 years. Our 2024 Congress, which is being held in Melbourne in July, is a collaboration with the Asian Australasian Society of Animal Production. We've had over 430 abstracts submitted, so it's shaping up to be a fantastic couple of days. And Associate Professor Fran Cowley will actually be delivering the Harry Stobbs Memorial Lecture at this year's Congress. So we're very lucky to have her here today as a bit of a sneak peek of what's to come at the Animal Science Congress. The AAAS also has a number of journal subscriptions that our members can get access to, as well as a monthly newsletter keeping you up to date on what's happening in all things animal sciences. I think on a personal note, I joined AAAS right at the beginning of COVID, and I found it a great way to stay connected with people outside of my own research group. And I'm really grateful for all the opportunities that I've had to contribute to committees, events, and activities and grow my professional network. If you are interested in joining, I've got some details on the screen. Something that you might like to share with your students is we do offer free undergraduate memberships and heavily reduced fees for postgrad students. Now, look, I think that's more than enough from me. I'm sure we're all eager to hear from Matthew and Fran.
Thank you very much, Joe, and thanks for sharing the presentation with us. If anyone has any question for Joe, you can use the Q&A function like we mentioned at the start of the forum. So we'll move on to our second presenter for today. So our second presenter is Fran Cowley, and Fran Cowley is an associate professor in livestock production at the School of Environmental and Rural Science within the University of New England, where she is a leader of the Ruminant research group. Currently, the focus for her research is nutritional solutions to methane emissions and carbon footprint of cattle and sheep. Thank you, Fran, and I hand over to you for your presentation.
Thank you so much, Ape. Thanks to Tia and AAAS for inviting me today. It's an absolute pleasure to talk about this topic in front of such a diverse and engaged crowd. I'd also like to follow up on Ape's welcome to country, acknowledgement of country by acknowledging that I'm joining today from the traditional lands of the Anawan people up here on the New England tablelands. But I'd like to take you back in time to start. So back beyond the settlement of Australia 70,000 years ago, back beyond the Cretaceous with the end of the dinosaurs, way back to what's more or less the beginning of time. And here we have around 3.5 billion years ago, life more or less crawled out of the primordial soup. In fact, at this time, it wasn't crawling anywhere. We weren't yet at the point of having legs. In fact, we were single cell organisms was essentially what life consisted of on Earth. So, in fact, life at this point in Earth's history was not even as sophisticated as bacteria are today. And what were the earliest forms of life were these organisms called archaea. Quite simplistic, but certainly life as we know it, but not life as perhaps you and I might recognize it when we think of our familiar life forms like animals, plants. So these were called the archaea. Archaea means the ancient ones, and I think it's so evocative as to where they actually sit in our timeline, but yet they're still around and having an enormous impact on our world today. So these archaea evolved at a time when there was no oxygen in our atmosphere. They evolved out of our ocean planet at that time, which had these highly acidic oceans. And the archaea, as the earliest form of life, they scavenged the oceans for those hydrogens that were causing a lot of that acid. And what they did was they scavenged the energy bonds between those hydrogen atoms, took those electrons, and they used that as a source of energy. Now, these archaea, in the process of utilizing those hidden electrons and hidden electron energy amongst hydrogen, they emitted a waste product, just as you and I and all animals and plants today emit waste products in the process of living. Methanogens also emitted a waste product, and that is methane. So methane does still contain a lot of these hydrogen atoms. You'll see it's one carbon with 4 hydrogens attached to it. These archaea are still around today. They're an incredibly diverse family of life. They are found in the soil. They're found on your skin, as you're watching me here today, in the digestive tracts of lots of different animals. They're found throughout our Earth. But we're going to focus today on one particular form of archaea, which are these archaea which produce methane as a byproduct of essentially their life form. So methane, it's a fairly simple product, a simple molecule, really quite small, but a really potent greenhouse gas. Methane has a global warming potential 28 times as great as that of carbon dioxide. So for every kilogram of methane that is emitted out into our atmosphere, we're getting 28 times the heating effect on our planet that a kilogram of carbon dioxide would produce. So somewhere a little bit further in time, it's still a fair way back for us, around about 4 million years ago, ruminants evolved, a group of animals which were able to find a niche in a also fairly recent grouping of life called grasses, where they could start to degrade the plant carbohydrates found in grasses by developing a symbiosis with some of these archaea, but also bacteria, fungi, and a whole heap of other microbial bugs. As ruminant nutritionists, they call us bucket scientists, and we just kind of group those all together as bugs because it's an incredibly diverse ecosystem in the rumen. Each teaspoon of rumen fluid can contain up to 1 trillion different organisms. And in a steer or a cow, we're looking at a rumen that contains over 100 liters of rumen fluid. So we're talking now about an ecosystem which is multiple orders of magnitude more diverse than the Amazonian rainforest, for example. So lots and lots of different life form interactions occurring in the rumen. We've got bugs digesting feed. We've got predatory bugs that are hunting out other bacteria and microbes. We've got herbivores, carnivores. We've got whole levels of trophic levels of food chains going on here. But the archaea play an important role in this diverse ecosystem where they mop up all the hydrogen which is floating around left in the rumen from the degradation of our plant complex carbohydrates into more simplistic carbohydrates called volatile fatty acids that our ruminant, whether it's a sheep or a cow, is able to absorb and utilize and turn into beef, milk, lamb, wool. So that animal can grow, reproduce, and live a happy, healthy, and productive life for us. So this excretion of methane by these methanogenic archaea also can represent a loss of energy to our microbes. To our animals. So the bonds that bind together those 4 hydrogens to that carbon, that's energy which is emitted out as a gas as our ruminants belch out methane and other gases from fermentation of their feed. And if we could find a way to actually capture that, then what the hope had been from the very earliest days, once methane was identified, was that we could actually capture that energy and turn that into productive purposes, redirect that from greenhouse gases into animal product. So although methane is short-lived, but the first thing you need to know is that methane is a short-lived product. So unlike carbon dioxide, for every kilogram of carbon dioxide that your life footprint has produced today, in 1,000 years, the majority of that carbon dioxide will still be in our atmosphere. But every kilogram of methane that our ruminants produce is only going to live in our atmosphere for around about 12 years before it is broken down, reabsorbed into soils and plants through photosynthesis, and then consumed again by our animals, and then, of course, cycled back out into methane again. So we have this really lovely cycle occurring. It's called a biogenic cycle because it's a natural part of life. So a lot of people talk to me about this and say, well, then why are we so worried about methane if it's a natural emissions and it's a natural cycling process that occurs? Well, part of the importance of methane is that cycle. Unlike the carbon dioxide that is produced from our cars, from our homes, from our travel, from our consumption, because that's out there in the atmosphere, we're kind of committed to everything that we've produced since industrialization started around a couple of centuries ago. But if we can start to inhibit methane from our ruminants and do that in a way which has a positive impact on animals, or at least not a negative impact, then we can actually start to use that biogenic cycle to strip methane out of the atmosphere and actually start to wind back our greenhouse gas emissions. So we actually can start to reverse our contributions to global warming if we can start to control methane emissions. On the other side of this coin is a really important, but perhaps a bit more somber note. Although the methane only survives in our atmosphere for around about a dozen years, the damage function, the warming that methane causes in that decade or so actually persists over hundreds of years. So if we don't do something about methane, we are still going to be contributing to long-term change in our climate, in our weather patterns, warming of our oceans, because that methane is causing damage, and that damage takes hundreds of years to dissipate in terms of the warming it contributes to our atmosphere, but probably more importantly to our oceans. So doing something about methane is really important for us as an agricultural industry to make a contribution to limiting global warming to that 1.5 degrees. So globally, enteric or rumen methane emissions contribute around about 10 to 12% of total greenhouse gas emissions produced by humans. So that is a significant chunk, actually. And in Australia, it's the largest single contributor to agricultural greenhouse gas emissions. So my team broke down where ruminant methane emissions came from within New South Wales. You can see here the vast majority, 99%, are coming from grazing animals. Most of it from beef cattle, about a third coming from grazing sheep, around about 7% coming from the dairy industry, and just about 1% coming from feedlot cattle. And that reflects the small number of animals that we have on feed in Australia at any one time. So around somewhere between 1 and 2 million animals on feed at any one time, and for a relatively short minority of their life cycle as well. in our Australian systems. Okay, so if we are going to actually do something about these emissions, if we're going to make our contribution to not only limiting global warming, but hopefully doing our best to reverse our committed historical greenhouse gas emissions, one of the things that scientists have been working on the hardest is trying to put feed additives into feed, whether that's total mixed rations or supplements, to try and actually manipulate the rumen production of methane. So today I wanted to go through essentially where we're up to with that process of development. This is probably the fastest moving area of science that I have been able to contribute to or even observed in my entire career. 10 years ago, no one was really thinking about methane very much at all. Starting around about 5 years ago, people started saying, oh, we probably should be starting to think about methane about a decade ago. And now it's full steam ahead. So we have come an enormous way in the R&D here in Australia, but also globally with around about 10 years worth of research and 5 years of really good hard focus. And I hope that you see today that Australia is actually leading the world in this field. So it's not the US, it's not Europe, even though there's a lot of talk comes out of Europe from about greenhouse gas emissions. There's a lot of money available to agricultural R&D in the US. It's actually Australia and New Zealand that have been making the largest contributions to actually get some traction on this. And it follows a fairly typical research and development and commercialization pathway. We start out essentially working in a lab. So it's expensive and it's quite hard to work with live animals. So you've got to start somewhere. So what we have is great chemists and biochemists taking rumen fluid samples from live animals, incubating that in water baths in a lab, and starting to put different products in and measuring the methane emissions as we keep those bacteria alive in a lab. Once we get something that has it looks like it could be positive, we need to get it out into live animals. So I can tell you a test tube in a lab is nothing like a live animal. So we need to get proof of concept in live animals. Often this is done with sheep because sheep are small, and when we haven't got a lot of product yet developed, we can feed a lot more sheep than we can with cattle. Sheep are a model ruminant, but I can tell you they are not a model cow. So once we have proof of concept, people very quickly want to start moving to cattle because, as you saw with that pie chart just before, the vast majority of our global emissions and our Australian emissions are coming from cattle. They're 10 times as big as sheep. Even though we've got more sheep, they produce about 10 times as much methane on a per head basis. So this live animal research generally happens in what's called the gold standard for measuring methane emissions, and this is respiration calorimetry chambers. These are photos of our chambers here at UNE. And actually collectively, these are the largest methane emissions measuring facility in the world. And the strength of Australian science about addressing ruminant methane emissions is reflected in the fact that the second largest methane emissions facility in terms of respiration gold standard calorimetry chambers is also in Australia. That's at Ellenbank, AgVic's facility down in Victoria. And the third largest is, an equal third largest is also in Australia at Townsville, run by CSIRO at Lansdowne Station. So Australia has been leading the world on addressing methane for a very long time. In fact, we started when the focus was actually probably more on the energy losses rather than the contributions to greenhouse gas emissions. So once we got some really good high confidence numbers around the emissions that we're getting from sheep or from cattle in chambers, we can start to refine the delivery mechanisms. For most of these products, there's a dose response. So the more product we add, the greater our methane emissions response is. And at some point, we need to get out into the real world. And so that's where we need to measure the productivity impact on our animals. So it's all very well and good having a high emissions reduction or inhibition rate. But if that has health or productivity impacts on our animals, if their live weight gain is going to slow, or their feed efficiency is going to blow out, or their milk production and quality is going to be affected, that's a really important thing to know, and that can be the death knell for an otherwise promising methane inhibitor. So that's when we start to go out into real production systems. Now, interestingly, a lot of the R&D at this point is done in feedlots. There's a couple of reasons for this. Firstly, we have a completely manufactured ration, so that enables us to make sure that every mouthful of feed that the animals consume also contains that methane inhibitor. So we're matching the fuel for methane with the inhibition process. Happy days. The next thing is that when we into feedlots, we can get really good replication, lots and lots of pens of cattle group fed in a fairly commercial setting. So we can start to get the statistical rigor that's needed to actually detect what are often biologically small but economically highly significant changes to productive efficiency. Thirdly, feedlots are considered globally to be a bit of the low-hanging fruit in terms of a business case for adoption of these inhibitors. So it's easy to include them into the ration. The ration's completely formulated, and it's easy to get a good effect. So we also have a global livestock industry which is dominated by North American feedlots and European dairy, both of which are a kind of a feedlotting approach or total mixed ration approach to feeding animals. So at this point, we've a little bit scanned on the kind of research that can actually start to deal with the majority of Australian emissions. So we're thinking about grazing animals. But whether we're in the feedlot or whether we're out, on a pasture, we can still start to measure methane emissions through some in-field mechanisms and equipment such as these. These are green feed emissions monitors. They're produced by a company called CLOC in the US. And you may have seen those around at research facilities, research stations, and even on some farms around you. They are expensive and they are temperamental babies, though, I would say. And while they don't give us quite certainly the level of accuracy and confidence that we get from the respiration calorimetry chambers, they certainly can give us a little bit of validation that we are getting emissions reduction in the field. And so we can deploy these into grazing paddocks or into feedlot pens, into dairies as well. And they also have sheep versions too. So we've had around about a good decade of research, as I said, 5 years of really hard effort, a lot of it led by Australia, but also contributions from our colleagues in Tasmania, in Tasmania as part of Australia, so across the Tasman, in New Zealand, and in the Northern Hemisphere as well. So where we're up to is we now have a bit of a basket of technologies, some of which have been superseded, others of which have not really quite made it. So I wanted to spend a little bit of time going through today where we're up to in terms of direct inhibition of methane with in-feed inhibitors. So the first one I wanted to talk about is nitrate, because it's probably one of the oldest. So nitrate is a relatively simple molecule. It competes with methane for hydrogen. So rather than having those hydrogens bound to methane, they're going to be binding to the nitrate. Now, any of you who are from a dairy production system background would be familiar with nitrate, though, for its toxicity. Nitrate poisoning on lush green pastures is a threat to all productive dairy systems after heavy rainfall. and rapid growth and warm temperatures. So you immediately, those of you from dairy systems, will be able to pick up what one of the weaknesses of nitrate is. It's that fact we can overdose our cattle and end up with nitrate toxicity and poisoning and cattle or sheep, and we can lose animals. Nitrate has actually been the first and in fact the only in-feed product which has actually been approved by the Australian government for an emissions reduction fund methodology. So you can go out today and feed nitrate and claim carbon credits on the basis of feeding that nitrate. Is this happening? Well, no. The logistical challenges and the safety challenges around feeding nitrate have meant that it's really been put to the side. Probably due for a revisit, perhaps, in some ways, and finding safer, more effective ways to feed it. But despite the fact it is an early proof of concept that we can manipulate the rumen microbiome, we can manipulate rumen emissions, at the moment, this is not really a practical strategy to use. The next one is what we call one of our tier 1 methane inhibitors, our big heavy hitters. This is a molecule called 3-nitrooxypropanol. It's sold as Bovaer and was produced by a company, or is produced by a company called DSM out of Switzerland. Now, DSM may be familiar to some of you from as a supplier of minerals and other feed additives for any rations that you're producing. So this is work that we did with 3NOP here at UNE, and as you can see, there's a dose response effect. The more you include in the diet, the higher your emissions reduction can be achieved. And we found that with Australian feedlot diets, we could get up to 90% reduction in methane emissions from our cattle. In fact, that 90% was actually statistically no different from zero. So we have almost complete removal of methane from our ruminants' emission profile. As we manipulate and vary the amount that we include in, and we start to change the basal diet, for example, to a more roughage-based dairy diet, the emissions reduction achievable is lower, so probably around about an average of 30 to 50% across all different production systems. So that's somewhat better than the 15 to 20% that we achieved with nitrate. So we can get really high responses with Bovaer or 3NOP, but again, it's very much diet dependent and inclusion rate dependent. The next thing that you may already be familiar with is Asparagopsis, or red seaweed. So this has a fascinating development story. It was actually, its anti-methanogenic properties were actually discovered here in Australia by CSIRO. And this is from a seaweed which is native to Australian waters, both the cooler waters around Tasmania, but also there are species of Asparagopsis up in the tropics in our ocean, in the the Pacific Ocean as well. So Asparagopsis is one of those which has also able to achieve around about 90% reduction in methane emissions, again in a feedlot ration. So highly promising feed inhibitor as well. Our next steps of where we go to though. So synthetic bromoform, that's taking the bioactive compound out of Asparagopsis and putting that in place, is one of the things that is probably the next thing that is going to be emerging. We have essential oils, whether they're lemon or cinnamon or garlic, or some commercial blends such as agalin. There's also research being put into a vaccine for a very long time, but it's very hard to vaccinate a rumen. It's just an organ designed to be colonized by bacteria. So that one's probably a lot further off. And then we also have probiotics available to us as well. Probiotics is something which so far has not been as promising as we hope. But with emerging gene editing technology, there's now the opportunity to use some probiotics that already have potentially a positive productive impact. So use them as production accelerators and edit their genetics to actually target those methanogenic archaea. So that's one of the things that we are really hoping to get to. So in terms of where we're going next, we've got a number of different products available to us. None of those are commercially available yet. A lot of those are quite some way off. Our real challenge, though, now is to get out of those intensive total mixed ration systems and get out into grazing systems. And that's where Australia really has to stand up, because it's not important to the Northern Hemisphere. It's really Australia that's going to lead the solutions in grazing systems. And I look forward to coming back and speaking to you not too much longer, perhaps in a couple of years' time, with some great solutions for grazing systems.
Thank you very much. Thank you so much, Fran, for that wonderful presentation. I believe that we'll have more time to discuss your presentation during the question and answer section session of this particular forum. And so, if anyone has any question for Fran, do kindly put them down in the Q&A function. So our next speaker, last for today's webinar, is Matt Harrison. Matt Harrison is an associate professor at the Tasmanian Institute of Agriculture and also the director of the Carbon Storage Partnership. His work focuses on developing sustainable pathways for balancing land use priorities in food security with those in environmental stewardship. He works with farmers, industry, and government to reduce greenhouse gas emissions while adapting to climate change in a profitable, inclusive, and socially acceptable way. Thank you very much, Matt. I hand over to you for the presentation.
Thank you, Abate, and thanks very much to the AAAS and TIA for the invitation to present. I acknowledge the traditional custodians of the lands throughout Australia and in Tasmania, the Palawa people, and I acknowledge the elders past, present and emerging. I also acknowledge funding from Meat and Livestock Australia, as well as a whole bunch of other organisations there at the bottom of the screen. Because I was last, I thought I'd present the key messages first and then present the underpinning evidence for those messages. So if you listen to nothing else in my presentation, this is the one slide to listen to. We ran a national analysis, so that was a high resolution, spatially explicit analysis of where carbon is in vegetation throughout the country in the red meat sector. And we showed that national livestock emissions have reduced by about 70% since 2010. That's mainly due to avoided deforestation. I'll go into that shortly. We did an extensive meta-analysis of the peer-reviewed literature, and we showed that over the long term, differences in grazing management had relatively little impact on soil carbon. That was not significantly different to zero, but results are very much contextualised and site-specific. We've done quite a lot of research on silvopastoral systems, experimental research basically with trees and pastures, and we showed that tree alleys were more conducive to greater pasture production as opposed to uniform block planting of trees. In terms of planting trees on a typical livestock farm, we showed that actual trees had the greatest relative reduction in greenhouse gas emissions, net reduction, and the greatest positive benefit for biodiversity, but they also had the greatest negative impact on productivity. And so really, I mean, the challenge for any land manager is what interventions, what changes do you make to the farming system so that it maintains or improves productivity and profit? At the end of the day, a farm is an enterprise. It improves biodiversity because land is finite, and it reduces greenhouse gas emissions. So it's not necessarily that easy. In terms of win-win-win-win that actually do all of those things, whole farm planning can do that if you strategically fence off areas for regeneration, but very, very much depends on your existing conditions and historical management and historical climate relative to the benefit that can happen going forward. We showed that lamb growth rates in the south, so if you fatten up lambs faster and sell them earlier, you avoid enteric methane. In the south was probably most beneficial for productivity and profit, in contrast to the north, which adult mortality of cattle in the north probably could be reduced a little bit, and that had the greatest impact on productivity. But again, very much depends on where you start. And really, consideration of multiple dimensions holistically and at the same time, so economic, legislative, practical, social, all at the same time, were more conducive to improve sustainability as opposed to myopically focusing on one thing, which tends to be easier, for example, economics. So just a quick overview of the Carbon Storage Partnership. The aspiration is a 10% improvement in livestock productivity between 2019 and 2025, and the equivalent of 15 million tonnes of CO2 equivalents stored in grazing lands. There's really three main areas that we're working on. So research and development in forages and in trees, silvopastoral systems. We're doing a lot of integrated management systems, so enabling tools, carbon accounting, natural capital dashboards, for example, and also communications and extension. So we're developing a training package that will compartmentalise all of the research that we produce in the Carbon Storage Partnership so that we have legacy after the program finishes in 2025. We have 6 different modules within the Carbon Storage Partnership, and an associated module. Sustainable Pathways to CN30 is led by UTAS, and that's that holistic thing about how do you improve productivity, profit, biodiversity, and reduce emissions. We have 3 dedicated modules on soil carbon, quantifying soil carbon at scale, as well as management practices to improve soil carbon, such as time-controlled grazing. We have 2 modules on trees or silvopastoral systems. So one is experimental, stake and wood, and that's silvopastoral systems. The other one is sort of social science, economic and modelling, and that's led by University of Melbourne. And there is an associated module, which is not part of the Carbon Storage Partnership, but linked with, that's called From Method to Market. So how do we overcome technical and economic barriers to improve landholder participation in carbon and ecosystem markets? So the first question we wanted to ask in the Carbon Storage Partnership was, where are we today? And how has national red meat sector greenhouse gas emissions changed historically? The aspiration is carbon neutral 2030, MLA's CN30 initiative. So it's important to know where we are today, as well as the impact that we've had, and I'll talk about that at the end. So we did a high resolution, spatially explicit analysis that accounted for all of the different land uses in Australia. And this was led by Dominic Bowen-Butchard at the University of Tasmania. This is an aggregated figure that you can see here, and it essentially shows that the highest net emissions, well, the lowest net emissions per hectare are sort of in the extensive zones, as you could imagine, South Australia, Northern Territory, the extensive regions of WA, and the highest emissions per hectare pretty much in the south of the country, where the sheep are concentrated in the country, so southwestern WA, the Glenelg Hopkins region of Victoria, and the Midlands of Tasmania. That result mainly driven by stocking rates, so animals per unit area. That's pruning out metropolitan areas and everything else. But it also was contributed to by sinks as well. So you can see that sink capacity in Gippsland there, the southeastern side of Victoria, was pretty low. So it sort of contributed as well. So in terms of the question that we posed, how have livestock emissions changed? Now, this has been done before, but this analysis was higher resolution and more detailed than has been done hitherto. So it has changed from about 155 million tonnes of net greenhouse gas emissions in 2010, about a 70% reduction to 2020, and that's mainly associated with avoided deforestation. It's worth noting that there's a lot of regrowth and deforestation and recovery, so sinks and forests are sort of coming and going over the period. So that's satellite imagery picking that up. You'll notice, and this segues well with Fran's presentation, that the blue bars there, the enteric methane, are stubbornly persistent, and they haven't really changed since 2020. So given that the net emissions associated with grazier forests have pretty much disappeared, the challenge now for practitioners and researchers will be to reduce that enteric methane portion at scale. The second part I want to talk about was our work in soil carbon, and really, France come up with this thing called the 4 per mil initiative, which was if you had a 0.4% increase in soil carbon globally, it would suck all of the atmospheric global CO2 emissions out of the atmosphere. So it would completely offset it. It's theoretical. You can never really improve soil carbon ad nauseum sort of thing, and it really depends on where you do it and where you start off from. But that's the notion. An incremental gain at scale would remove a massive amount of CO2 from the atmosphere. So one way we're sort of working on that is through Perennial and Farm Lab and NASA in the US through high resolution satellite imagery, which is really to improve the analytics for modelling soil carbon. We have different models to sort of stratify at the regional level to say which areas are high in carbon and which areas are low, to give an indication of how soil carbon might be improved. And then we have higher resolution models at the farm level, which is called stratification, which determine where you should go out and take a physical sample. And really the whole aim there is measuring soil carbon, sending people out in the field is costly and time consuming, is to improve the predictive power of modelling, satellite imagery to reduce the costs of physical sampling. We also did a meta-analysis, and that was published in the Journal of Environmental Management. And really, probably the conclusion of that, and that looked at a whole bunch of peer-reviewed publications, more than 105 comparisons. And over the long term and across all of those studies, and this was focused on Australia, there was no significant impact of grazing management on soil carbon. So high intensity versus low intensity, continuous grazing versus rotational grazing, for example. But the other point to remember is it's very much site specific. So pretty much depends on where you start from, the capacity to improve soil carbon. The other part that we're focusing on is silvopastoral systems, so trees and pastures, and that's led by QDAF. So we're looking at, this is an experimental study, we're looking at alternative tree configurations, trade-offs between pasture and wood production, financial implications, carbon sequestration and biodiversity. So we're looking at, well, can we thin trees out? What happens to tree growth and pasture growth if you thin them? What happens if you improve the pasture? What happens if you leave the pasture in its native state? We're looking at different row configurations, so double planting or triple planting, as well as different alley lengths. And if you just compare the left and the right photo there, you can see that there's a significant difference in the pasture production. Like the photo on the left is 350 trees per hectare in a 12-metre alley, and the one on the right is 100 trees per hectare in a 20-metre alley. And when you quantify that, you can see that there's a massive difference between pasture produced, up to 225 trees per hectare in the alley configuration. And then as you increase the tree density, pasture production sequentially diminishes. But you can see the blue bars there are significantly lower. So tree configuration does have a very significant effect on pasture production. At the end of the day, pasture is the cheapest form of feed. So you really want pasture production as well. And the final part that I wanted to talk about was these holistic changes to farm systems or interventions with the aim of improving profitability, because a farm is a business. It's important to remember productivity, because at the end of the day, we need food security. We've got greenhouse gas emissions to think about. We've also got biodiversity and increasing interest in natural capital. So to do that, we're using real farms, real case study farms across Australia, and these are positioned in each of the agroecological zones of the country, as well as and are characterised by a range of different production systems. So just for example, if you look at CAC2 there, just above Brisbane, it's about 1,100 millimetres of rain per year, which is very high, and only 750 hectares. And if you can compare that to the farm in the centre of the country, that's pretty much in an arid zone, 160 odd millimetres of rain a year, which is very, very low. And it's nearly 500,000 hectares. So the scale and the labour and the capital and everything else very much dictates the ability of these farms or enterprises to implement any of these interventions. One of the things that we've found, we're doing spatially explicit carbon and biodiversity for each of these farms, and one of the things that we've found is a long-term decline in biodiversity and carbon stocks, mainly on the farms near the edges of the continent or the intensive ones. The ones in the centre of the country, so CAC5 to CAC7, have positive changes in biodiversity. Now, this is only a very preliminary result, and so I wouldn't take it as granted sort of thing. It could be due to death of isolated trees. It could be an artifact of the analysis. It could be due to land clearing, don't know, but it's interesting that it's coming up that way. When you actually look at each of the biodiversity indicators that we quantified, you can see that those biodiversity results in effective habitat condition are pretty much biased just by a few pixels there, that image in the bottom left-hand corner of the screen. So it's only a few that are influencing that result. When you look at carbon stocks over the long term, absolute carbon stocks for that Tasmanian farm haven't really changed much. So we quantified above ground biomass, below ground biomass, and dead organic matter. And most of the change in soil carbon sort of occurred around 2007 to 2011, and with less changes in recent times. So we're sort of looking into why that might be as well. So to come back to where I started off with, what interventions do we have? And because we've got different farm sizes and different agroecological regions, a way to standardise it, we thought, was, well, if you plant 10% of your arable grazing area with trees and you dynamically simulate carbon sequestration, how does that impact relative net farm emissions? So is it a 2% decline in net farm emissions, or is it a 15% decline, for example? We're doing that spatially explicitly at a pixel size of 25 square metres and aggregating that over 25 years. So it's a very detailed study. There's a lot of numbers underpinning these figures I'm showing here. Just to give you an indication, for example, the farm in the north, the Northern Territory one, after 25 years had an average carbon sequestration associated with planting trees of about 38 tonnes of carbon dioxide per hectare. Whereas the farm in Tasmania, which had similar rainfall or even slightly less, had 110 tonnes of carbon dioxide per hectare, so significantly higher. So really, probably the point I'm trying to illustrate there is that climate and soil types very much influence, it's not just rainfall, but all of these other factors influence your ability to sequester carbon. Now, this figure is a little bit of a horrendogram, and it's not that some of the numbers are not finalised. The only thing I really wanted to say was that they point out the green dots there, and any of those points that align with the origin, the 0 point, essentially the baseline. So we sort of showed that planting trees had the biggest impact on net farm emissions, but that could have been associated with the assumption of planting 10% of grazing area. So they actually had a greater impact on net farm emissions compared with enteric methane. We didn't assume the high value numbers that Fran presented. We assumed sort of a more representative number out of the literature, I guess. So I think we used 17 and 37%, assuming animals would be away from the feeders and eating other things as part of their normal routine. So interventions that improved live weight gain of young animals, lambs in the south, were most beneficial because that avoided enteric methane, and interventions that reduced adult mortality, so death rates of adults in the north, were most beneficial. So again, really illustrates the point of looking at farms across agroecological region, and there's really no panacea. So was there any intervention that improved biodiversity, productivity and profit and reduced emissions? Well, whole farm planning sort of did that, but again, depends on where you start off with. One farm, for example, had too many wallabies, I would say in pest proportions, and the farmer suggested that we fence off the native woodlands to keep those, fenced off in silico this is, not in practice, fence off the woodlands to keep the wallabies off, and we actually modelled the impact of that on pasture production and soil carbon, and we showed, well, the pastures come back, it sustained increased live weight gain, and it improved biodiversity. So that technically was a win-win-win-win. Others, not so much, which is pretty much what you'd expect. Some improved biodiversity, but were costly. Trees, for example, were a good indication. They reduced emissions in a big way, but they were relatively costly. So I think the cost of trees was between 90 and 100 tonnes of carbon dioxide equivalents. If you compare that with a carbon spot price of $35 a tonne now, you can see that the economics are not really in favour of carbon sequestration, but there's a whole bunch of non-monetised ecosystem services in there, like pollination, aesthetics, appreciation of property value, reduced fire risk. So if you accounted for all those, well, the economics may change. The other thing I want to mention just quickly was that what I call the sequestration versus mitigation conundrum. And if you planted trees, say in year 0 there, you'd get something like that red curve, or if you made some intervention to improve soil carbon. So it increased at the start, you hit what's called an inflection point, and then it tails off, so it plateaus. In contrast, enteric methane, assuming all animal numbers stay the same, just keeps going up linearly. It won't change unless you change animal numbers or do a feed supplement or whatever. So if you're wanting to get to a net zero position or a net zero enterprise, well, your carbon sequestration is going to go down over time, whereas your methane emissions are just going to keep going up. So the ability to maintain a net zero position becomes harder and harder unless you keep changing. The other thing to point out is that if you reduce enteric methane, well, that will be cumulative. So that happens year on year, assuming that they eat it. So that abatement will continue year on year. The other thing you can do, and this was shown by Rod Keenan and Rochelle Meyer at the University of Melbourne, is asynchronous planting. So all of these are 20 hectares of trees, except the green curve is 20 hectares in year 1, and the grey curve is 1 hectare per year for 20 years. And you can see they're very different carbon sequestration curves, and so they have very different impact on your ability to get a net zero farm business. The other part that I think I should mention is the co-benefits of trees on farm. I sort of did go into this before, but a good example is the productivity co-benefit. So if you have a shelter belt and you have lower lamb mortality, you have a productivity gain and you have an improvement in profitability. Rochelle Meyer did a big survey of farmers in Victoria, and one of them said, shelter is the most important thing for any lambing ewe. Even if the ewe is in good condition and she has lots of food, it won't save the lambs from a bad weather event if there's no shelter. So they looked at the economics, and I think I mentioned this before, but it's $96 to $106 per tonne to recoup the costs of planting trees. So it's quite costly if you compare that with about $35 a tonne spot price in Australia now. And there's a whole bunch of other non-monetised benefits that, while not monetised at the moment, probably will be in future. And so this comes back to this thing that we developed and published in 2021 called carbon myopia. The position of society at the moment is on global warming and therefore carbon, and sort of myopically focused on carbon. But at the end of the day, land users have to think about biodiversity, productivity, profitability. They have to think about air pollutants, overconsumption, education, and everything else. And so to that end, we're developing a national natural capital dashboard, which gives a quick snapshot of where the farm is tracking, so emissions and natural capital and biodiversity. And farmers can use that in real time to say, well, how am I tracking? What do I need to improve on, sort of thing. The final thing that I will end up on, and I don't show whether I should have finished or not yet, but is the monitoring and evaluation and learning, which is we have a dedicated adoption coordinator for, and that's led by South Coast NRM and WA. The reason for that is to say who have we engaged, what have they learnt, what do they perceive as most valuable, what should we be doing more of, what should we do less of. And I did note the poll at the start of this webinar, so hopefully this is part of that. We've monitored engagement since the start of the Carbon Storage Partnership through field days, panel meetings, presentations, and we have engaged interactively. And that means you talking to me and me talking to you, 21,000 people, which is significant. And if you put a conservative, highly conservative estimate on that, that's worth about $57 million or more than 2.5 million tonnes of CO2 since April 2021. So I'll stop presenting there, but happy to take questions, and thanks again for the invitation to present.
Thank you very much, Matt. That's very wonderful insight that you've provided to us today. And so we'll now get into the questions and answers for the forum today. And we have some quite a collection of good questions that we'll go through in this session of the forum. So I'll start. I think this is for Fran. There's a question here that wanted to know: do the GHG emissions for New South Wales that you have shown reflect the values for Australia more generally?
Thanks for that, Ape, and Michael, for your question. Yes, that's a really great question. New South Wales is a very nice example of, I guess, what my kids would call the medium state in this scenario. So it is not a bad representation of Australia's emissions as a whole. Cattle emissions, once we take into account northern production systems, probably do bump up over about 60% of the contribution of enteric methane emissions. And dairy takes a slightly smaller proportion once we think about states which have a smaller dairy industries than New South Wales. So it's probably more of a movement of emissions from sheep and dairy into cattle, but it's not too far off the Australian profile. But of course, this does change from year to year based on season, based on the national herd, while dairy herds don't change and tend to be relatively stable regardless of season and climate conditions. Cattle and sheep herds and flocks, of course, can get scaled back significantly and built up again. And so the number of animals we have in our national flocks and herds is really what drives that breakdown of sources of enteric methane.
Thanks, Fran. Is it possible to breed for reducing methane? I'll throw it back again to Fran, and probably Joe, who is a geneticist, might also want to add to this as well.
Maybe I should let Joe answer.
Okay.
I'm happy to answer, but Joe, I think you probably...
Fran, I'll let you start off, and then maybe I can add a dairy perspective on the end.
Okay, so absolutely. So we do see around about a 30% variation between individuals in their baseline methane emissions on the same diet. And the good news is that methane emissions have a relatively good heritability. Joe will correct me if I'm wrong, but off the top of my head, it's around about a 20% heritability. So that tells us that while the vast majority of variation in emissions is sourced from other things such as the diet, the environment, other issues, there is significant variation, but also significant ability to pass down a low methane animal to its offspring. Joe, do you want to talk about the work that's being put into place currently?
Yeah, thanks, Fran. You're right. I usually say that around 15 to 30% heritability, because there's obviously variation between species as well, and what definition of methane is used. So I think that's really exciting in terms of methane emission, the opportunity to develop a breeding value, so a tool to identify animals who will produce progeny that have lower methane emissions over their lifetime. And I know that that's a big focus area for a number of groups at the moment. But I think one of the other opportunities in terms of can we breed for methane emissions, when we're breeding for animals that are lasting longer, that are getting back in calf quicker, that are more feed efficient, we're also indirectly selecting for improved methane efficiency. So the dairy industry has a tool called the Sustainability Index, which was released in 2022, which does just that, takes economically important traits for dairy production and adds additional emphasis on the traits that we know are associated with improved methane efficiency.
Can I just ask there, Joe, how easy is it to get maladaptation? So you breed for an animal with reduced methane, but then you find out I've completely wiped out marbling or growth rates or something else that was desirable that's disappeared.
Yeah, no, that's a great question, Matthew. And I think the classic example from the dairy industry is when we first started to breed for, improvements to production. The only thing that we were measuring on dairy cows was like that milk yield and milk traits. And the unintended consequence of that was that fertility declined. But the positive news story is that now that we know there's a negative genetic relationship negative genetic correlation between those milk production traits and fertility, we can measure it, we can monitor it, and the dairy industry has been successful in reversing that decline in fertility over the last 5 to 10 years. So I think we're in a much better position now than we were in the 1970s in terms of being able to carefully monitor any other unintended consequences.
Okay.
Thanks, Joe, for that response. Matt, I'd like you to respond to this question. Should farmers focus on carbon, biodiversity, or livestock production?
That's a good question. Depends on your motivation. So an example would be if I had a more ecological bent, and I was a farmer and I wasn't interested in profit or productivity, I would revegetate the land and get rid of livestock, and that would reduce methane emissions in a big way and sequester a lot of carbon and improve biodiversity, but wouldn't feed the world if everyone did that. So on the other hand, you could have a feedlot, which is just animals, no trees, no biodiversity or anything except for the animal microbiota sort of thing. So it depends on what your motivation is. I think for the average, if I can put it that way, family farm, you might want to think about what areas of your farm are unproductive that could be used for revegetation, like a gully or a fence line, for example. How do you get the most out of productivity? Grass production, which is the cheapest form of feed, and also carbon sequestration as well. So basically use the tools you have and the available knowledge and talk to the experts sort of thing.
Thanks, Matt. Fran, during your presentation, you showed some products that are currently in use. Which of these products is closest to market?
So probably the product which is closest to market is Bovaer 3-NOP. It's actually being used in some feedlots and dairies in Australia already. However, supply is very limited, and DSM are actually constructing a brand new factory in Scotland to supply the global demand for this. Asparagopsis, of course, is growing now, but all of these products, the challenge for them is trying to get sufficient quantities available and at a price which can drive adoption. So some of the products that are emerging or are close to the point of commercialization are maybe 1 to 2 orders of magnitude more expensive than they need to be economical, given our current balance of incentives, price of carbon credit units, and so on. So then what I really think needs to happen in order to get widespread adoption is we need to have a better balance of incentives, and that probably means some policy carrot or potentially stick to reward farmers for essentially expending money. One of the early secondary wishes of inhibiting methane was that if we can capture that energy which is lost in gas emissions and convert that into animal product, we can actually get improved productivity. So a co-benefit which will offset the cost of feeding any of these inhibitors. Now, sadly, that has not really emerged so far to date in wide-scale trials. We do think that most of the energy is still being lost through essentially through hydrogen gas going off as H2. So the challenge that our scientists have now in front of us is how can we better capture that lost energy and redivert it into something that animals can use. So currently, although the potential is there in theory, the chemistry and fundamental biochemistry doesn't add up yet to help us have a strong expectation we're going to get a productivity co-benefit. And when we look at the data from wide-scale trials that are being put in place, we're not seeing a gain in productivity. However, there are some emerging signs that there could potentially be some improvement in feed efficiency, but often these are from reduced intake rather than from improved live weight gain. So animals either maintaining their live weight gain or perhaps having a slight reduction in live weight gain or milk yield as an alternative, but eating less. So that is not quite the most positive story that we would hope to in the most rosy best case scenario, but there's something there that we can work with. And so some of the research that we're starting to go through now, we have a new zero net emissions for agriculture, CRC, just started here in Australia. And one of the big focuses of the research in that CRC is going to be how can we start to stack technologies, including ones which can help capture this lost energy, which we're now saving from methane, but not yet finding a way to redirect to productive purposes.
Can I just ask a follow-up question to that, Ape? Hopefully I'm not interrupting. Fran, the challenge, supplements all very well in intensive zones where you can access and manipulate the diet on a daily basis sort of thing in a small paddock. Some of the farmers in extensive zones, they might not see their animals for a whole year and they drink out of water holes and stuff. So one farmer we worked with did a second muster with a helicopter and just found another 1,000 animals in the bush sort of thing. So they don't see them that often. How do you use a feed manipulator or supplement or inhibitor in that type of environment, or can you?
That is the big question, Matthew. And currently we don't have anything right to hand to really deliver these inhibitory supplements to grazing livestock. So the research that I had presented was mostly around feedlot or intensively fed dairy cattle. And even with grazing dairy cattle, they're coming in twice a day and we can give them a supplement in the bale, right? With grazing cattle, that is the number one challenge for the Australian livestock industry, really. There is some research that UNE's has been started over the last couple of years trying to get these supplements into pellets, into liquid supplements and into lick blocks to that. We're actually now at a point where, yes, we know some of these supplements will work in, some of these inhibitors will work in supplements, but then there's still a massive leap to get from that point out to getting those supplements down into the rumen of our grazing animals. A lot of the big the high achiever inhibitors that I showed, such as Bovaer and Asparagopsis, have a really short duration of impact in the rumen. So they only inhibit methane for maybe an hour, maybe 2 hours at most after those inhibitors have been consumed. So for grazing animals, where all the fuel for methanogenesis is obtained in the hours and hours later on when they're out grazing in the paddock, this doesn't really work. So things that are being tried are, for example, boluses made of biopolymers or traditional type boluses containing compacted high intensity products or high concentration products, trying to get supplements that work within production systems, such as a lot of extensive production systems do have mineral supplements, for example. Can we work with current practices? But these are all really, really difficult challenges. And right now, our ability to inhibit emissions in grazing animals, even intensive grazing animals, is really quite constrained and is the absolute focus of the Australian research community right now. That's even not even looking at extensive systems. I think for those extensive rangeland systems, the herd management techniques that you mentioned, Matthew, are probably the low-hanging fruit for those production systems. Let's reduce our empty and dry cow stock, for example, that are spending their lives eating our grass, emitting greenhouse gases, and not giving us calf yield in return.
Thanks, Fran.
Thanks, Fran. I just want to take you back to the impact of the technologies that are available at the moment. You've mentioned impact on production. Is there any update on health impact as well, or not?
Yeah. So far we haven't seen any, so most of those products that do have an impact on health get weeded out pretty early on. In that research development commercialization pathway, that's one of the first things that we look at, intensively sampling blood, rumen contents, and also carcass for any impact on residues or animal well-being. So all those ones which are emerging as high, as have high potential, have passed that threshold now.
All right. Matt, Question for you. Are there some regions that are more amenable to livestock production through carbon sequestration than others?
Yeah, it's a good question. We sort of started looking to that. Depends on how you define it. The carrying capacities are certainly higher on an area basis towards the edge of the country, where at the continental scale, where you get more rainfall and less so in the centre. But on the other hand, near the edges of the country, you can grow crops, and you can't grow crops in the centre of the country because rainfall's too low, and so therefore suitable to livestock. So hence the people who lament livestock production and sort of say that livestock are greater land users. Well, that's because they're promulgated on areas that you can't grow crops. Similarly with water use sort of thing, rainfall falls on the land and it will fall there one way or the other, but people use that to characterise water use associated with livestock, but it's going to fall one way or the other. So good question, Ape, and I think again the answer to that would depend on where you are.
Thanks, Matt. Fran, I guess this is for you. How does the reduction of methane emission in ruminant affect the fate of CO2 and hydrogen gases within the ruminant environment? Can the technique reduce or eliminate belching of CO2 and hydrogen at the same time?
Yeah, great question, Ape. What we have actually found from our research is that when we are able to achieve those really high levels of inhibition, 90% plus of methane abated, what we're seeing is that eructated hydrogen is actually going through the roof, 15, 20 times what we see in the control animals. So that's pretty clearly to us the current fate of hydrogen. The original idea had been, if we are actually going to block methane from being synthesized, can the hydrogen actually be turned into propionate? That would be the best case scenario. Propionate is the source of all the majority of glucose in our ruminant metabolism. But what we find is that it's actually really difficult to achieve that. What we're trying to do now is to feed essentially paired inhibitors or supplements. So we have a direct inhibitor of methane, and then we have an alternative hydrogen sink, such as a precursor like fumarate or succinate, which is further back up the propionate pathway and can accept those hydrogens instead and hopefully redirect them to a more productive endpoint. But at the moment, what we're seeing is that hydrogen is mostly being emitted out as H2 gas. Carbon dioxide, generally not affected. We're really looking at hydrogen accounting and the hydrogen economy in the rumen when we're looking at methane. CO2, we actually want CO2 to be relatively high in the rumen because that reflects that we have a really cracking rumen fermentation happening. Just as CO2 gives the bubbles in beer, the more fermentation we've got happening in the rumen, the more digestion of our feed for our animals, then the more CO2 that we can produce. So that's not something that we want to start going manipulating.
Yeah. Anyone can respond to this question, and I think it's important. How are our trade partners responding to the potential options of methane mitigation, for example, gene editing, potential chemical residues, and so on?
Well,
anyone can answer that.
I'm happy to take that one, Ape. So I guess Australian agricultural industry, as a very export-focused industry, is always looking at what our trade partners are demanding. And a lot of the drive amongst our peak bodies in Australia to achieve carbon neutrality is around ensuring that we are maintaining our market access and starting to expand our market access into those trade markets such as Europe, who are more and more looking like they are going to start restricting access based on emissions profiles. So Australian producers, I find, are extremely pragmatic. Other parts of the world that are more insular and domestic focused might argue about their opinions or ideology on various aspects of livestock production. In Australia, we're very much like, I want to sell my milk, my wool, my beef. What have I got to do I'll give the customer what they want, and we are very much outward focused and pragmatic in that respect. And so I think that's a real credit to Australian producers who knuckle down and do what needs to be done in order to be essentially feeding the world.
I might follow up there.
Yep.
In 2021, Joe Biden said that if you haven't got an emissions mitigation plan in place, we will tax your imports. So if, similar to emissions standards for cars, if we don't have something in place soon, and it's not enough to have something in place, you have to be seen to be reducing it as well. So, I mean, the bigger corporations like Nestle and JBS and Greenhams have all got these emissions mitigation plans in place, and they've got aspirations for carbon neutrality by a set time, 2030 or 2035 or 2050 or whatever it may be. So the bigger corporations are sort of doing it. The supply chains like Woolworths and Coles are also doing it. Individual farms vary quite a lot. So some farms, a lot of farms are either doing nothing and we're sort of waiting and watching, being quite cautious about carbon markets. Some people are selling their carbon. So once you've sold it, you can't claim it in an emissions, low emissions product. So low emissions beef or carbon neutral beef, for example. And some people are insetting. So that's the same administration, but you have it audited, and then you get the carbon credits and you keep it. Then you offset it against your net farm emissions, and then you can claim a low emissions product then. So meat, milk, wool, or eggs, for example. So sort of depends on where you are, but the larger corporations are onto it now. So it's very important, not so much methane, but emissions in general.
Thanks, Matt. Thanks, Fran. If we could feed a supplement to reduce methane production by 80 to 90% in extensive beef or grazing system, should we expect them to grow more efficiently?
Yeah, great question, Ape and David. What we have seen so far is that just haven't got that ability to capture that energy and turn that into productive purposes yet. Now, we've done quite a bit of research at UNE, particularly in feedlot systems, because, as I mentioned, that's the low-hanging fruit, but also where we can start to really measure at a statistically significant level the changes in animal productivity and efficiency. Now, when we fed Asparagopsis oil to cattle, we saw a reduction in dry matter intake. So that ranged from 5 to about 8% reduction in dry matter intake, and persisted over up to 275 days in the case of long-fed Wagyu. So a lot of people might look at that and go, palatability problem. As a nutritionist, I don't believe in the concept of palatability. Rather, taste is just a way our brain shortcuts of the positive and negative feedback of, did this make me feel good? Did this make me feel full? Did this make me feel a bit off? So when we see this low reduction feed intake persisting over hundreds of days, it's not a question of novelty, of eating something that tasted unusual, and so the animals avoid it. Particularly in a feedlot, we've got animals have nothing else to eat. They can't go and say, oh, I'm going to go and eat that bush over there if I don't like this grass. So what we're starting to come around to now, as we see this evidence accumulating across a number of research trials, is that we think actually that accumulation of hydrogen might actually be prompting satiety in the brain. So animals, they feel full. Now, when you're out in a grazing system, that feeling of satiety becomes even more potent, because grazing has significant costs to the animals. You're out there in the exposed to the sun, to the elements. If you're a herbivore, you're thinking constantly, am I at risk of predators? What else could I be doing rather than being out in the heat grazing? So if we start to have really high levels of methane emissions, and we can't find some way to redirect that hydrogen, potentially we could see quite significant reduction in feed intake in grazing animals. Whether or not we actually get an improvement in efficiency, though, in reducing that, maybe reducing intake, but maintaining productivity, The research is mixed so far. It's early days in terms of getting that evidence up at significant scale. But I'm pretty confident that over the next, actually over the next couple of years, we're going to start to see new technologies coming out, new nutritional strategies that can actually help to overcome these limitations, maintain feed intake, and potentially hope to get some improvement in efficiency. Of course, in extensive grazing systems, the challenge is always going to be getting these inhibitors into the rumens of our animals and doing so in a way that's going to be cost effective for producers. But in a hypothetical world, there's still some way to go.
Thank you very much, Fran. I'd like to just take one more question to be answered in a minute by Matt. What is the potential for planting trees and carbon capture in both maintaining animal production? If you can answer in just a minute, thank you.
Yeah, that's an active area of research. I think it's a really good question, very much site specific and depend on what sort of the productivity of your land and what areas could be viably planted without taking away pasture production, which would reduce carrying capacity sort of thing. So fence lines and gullies and that sort of thing. The co-benefits question is a good open area for research. I think co-benefits for productivity, ecosystem services, income from biodiversity, appreciation in property value. 4% of the farm planted to trees will appreciate your property value by about 10%. So there's all of these non-monetized factors. So I think planting trees on farm is an area that deserves further consideration. If you had a large woodland on farm already, which some farmers we work with have done, what's the potential for thickening up those woodlands, not taking away pastures and increasing trees, environmental plantings on those zones? So it's a good question, but again, comes down to site specifics. Thanks, Abate.
Thanks, Matt. I know that we still have some more questions, but looking at our time, we don't have too much time left for today's forum. So if you have any further questions for our speakers, the email addresses of our speakers will be made available along with the recording. So you can contact them when you get the email from us of the recording. I'm sure you can agree with me that we are facing a very huge challenge with emissions from livestock production and agriculture in general. But from today's presentation, you can also see that we are making progress and hopefully we'll continue to make progress towards reducing methane emissions and emissions in general in agricultural production and livestock production system in the coming future. So at this stage, I would like you to join me in thanking all our speakers for wonderful presentations and making our time worth it for today's forum. Before you leave, please take a moment to complete a short feedback poll that is being shown on the screen. We would really appreciate that you give us some feedback for today's webinar. Thank you for taking part in this event and enjoy the rest of your day.
Thanks for your efforts, Abate.